Hello, my name is Eric Rosen. I'm a third-year PhD student at Brown University, and I'll be talking about our IROS 2020 paper, Mixed Reality as a Bidirectional Communication Interface for Human-Robot Interaction. Communicating human knowledge and intent to robots is essential for successful human-robot interaction. For example, when a surgeon says, "Hand me the scalpel," it is crucial that the assistive robot hand over the correct utensil. In order to efficiently collaborate, humans intuitively communicate through noisy modalities such as language, gesture, and eye gaze. Failures in communication, and thus collaboration, occur when there is a mismatch between two agents' mental states. Question asking allows a robot to acquire information that targets its uncertainty, facilitating recovery from failure states. However, all question asking modalities have trade-offs, making choosing which to use an important and context-dependent decision. Previous research has investigated different communication modalities between robots and users, identifying the cost and benefits of each. A large amount of work has investigated physical robot actions to reference objects in order to communicate with a human user. Two of the most effective ones being robot eye gaze and robot pointing. Language has also been shown to be an effective means of symbol grounding. However, none of these approaches have actually compared how these physical approaches or language-based approaches compare to visual interfaces. Visual interfaces such as mixed reality have been shown to reduce mental workload and improve task collaboration in human-robot interaction. Related works have demonstrated the power of mixed reality interfaces in task settings like intent communication, trajectory programming, and navigation specification. In this work, we aim to close the gap of research on how mixed reality compares to physical actions for reducing robot uncertainty. In this work, we contribute a decision theoretic approach for mixed reality as a bidirectional communication interface for reference grounding. We also conduct a user study comparing physical behaviors versus virtual behaviors for question asking in order to reduce robot uncertainty and recover from failure states. We first discuss some background, where we define a Markov decision process in order to represent the environment. A Markov decision process is formally defined as S, a set of states, A, a set of actions, T, a transition matrix representing the probability of transitioning to a state S prime after taking action A from state S, and a reward function that returns a scalar value for a given SA S prime pair, as well as a discount factor for the planning horizon. In cases where the environment is not fully observable, we can extend the Markov decision process to be a partially observable Markov decision process, where we have an additional set of observations as well as an observation model that tells us the probability of receiving an observation conditioned on a certain state and action. This work investigates how physical and visualization-based question asking compare for reducing robot uncertainty under varying levels of ambiguity. To do this, we first model our problem as a POMDP, termed the Physio-Virtual Deixis POMDP, the PVD POMDP, that observes a human's speech, gesture, and eye gaze, and then decides when and how to ask questions in order to increase accuracy, and when to decide to choose an item in order to decrease interaction time. More formally, we define the PVD POMDP as the following. I, a list of all the items on the table, where each item I has a known associated pose, X, Y, and Z, and a set of associated vocabulary. Our state S is defined as two things. ID is the human's desired object, which is unknown to the robot, as well as Q, which is the last question the agent asks, which is always known and initially null. A is our set of actions, where we have non-question asking actions such as waiting and picking the actual item I, as well as question asking actions such as pointing to item I, looking at item I, or highlighting I using the mixed reality interface. Our transition function T represents that the desired object ID remains constant and that the question last asked Q changes deterministically with each action the robot takes. Our rewards can be described in the following descending order. Picking the correct item has the highest reward, waiting has the next highest reward, then using a highlight question, then looking, then pointing, and the most costly action being picking the wrong item. The exact reward values used in our experiments can be found in our paper. We decompose the observations that the robot can receive into language, eye gaze, and gesture, where language can further be decomposed into base and response language. Response language are words that correspond to things like yes and no for answering questions, whereas base language are all other words. In order to define our observation model, we make an independence assumption that each of these observation modalities are independent conditioned on the state. We will now describe how we define each of these components of the observation model. We'll start by defining the observation model for the base language utterances. At a high level, for each base utterance, we define a literal interpretation probability and a probability that the speaker chooses those utterances. More details can be found in our paper how we use this in order to define the observation model for the base utterance. We have a separate observation model in order to define the response language likelihood. For this, we define the probability of receiving a response and the probability of a human interpreting the question about an item I as item J for each type of the question asking modalities, and we define the probability the human responds correctly based on that interpretation. For pointing and highlighting, we use a similar likelihood observation, while for looking, we use a more complex observation model for how humans interpret eye gaze based on Admoni et al. More details can be found in our paper about the observation model here. Lastly, we discuss the observation model for the gesture and the eye gaze. Human eye gaze is modeled as a vector from the user's head to the point they're looking at. Gesture is modeled as a vector from the user's hand to the point they're looking at. Both of these can be calculated using the Mixed Realities API. Angles are measured relative to the vector ending at the desired item. When present, gaze and gesture are assumed to come from Gaussian distributions as described here. Due to the differing noise models combined with a decision theoretic approach, the robot considers pointing to be more costly than looking and thus will only point at an item when the increased accuracy is worth the cost. Roughly speaking, the robot will look at an item if it is far enough away from the other items that looking is unambiguous and will point at an item when it is in close proximity to the other items. In order to evaluate the PV-DPOMDP, we decided an evaluation task where the robot disambiguated what item the human referred to as quickly and as accurately as possible from an array of potential objects on the table in front of the robot. The aim of our evaluation was to investigate how communicating questions via physical robot behaviors like looking and pointing compare to communicating those questions via mixed reality visualizations. We devised a user study to compare 3 conditions of communication modalities. In the no feedback control condition, the robot did not ask any questions and only decided to pick an item when it was sufficiently confident based on observations from the human. In the physical feedback condition, the robot was able to ask questions by moving, either using gesture or looking to reference items. In the mixed reality feedback condition, the robot was able to ask questions by visualizing a sphere over the referenced item in the user's mixed reality headset. We posited 2 hypotheses about the objective measures and 2 hypotheses about the subjective measures. Here we show an image of our setup where a user is pointing at an item for the robot to identify and hand over. Here we show the robot pointing to an item in order to ask a question. Here we show the robot using eye gaze to look at an item. And here we show from the point of view of the user what it looks like when the robot highlights an item using the mixed reality interface. Here we show a video from the point of view of a user wearing our mixed reality headset, how an interaction looks. So the user can ask for an item and the robot can highlight that object using mixed reality. Here we report the results of our experiments for both the quantitative and qualitative results. And what we see is that across the board, the mixed reality condition is better than the control and physical condition. More information and analysis about these results can be found in our paper. To conclude, we present a decision theoretic model that we term the PV-DPOMDP for interpreting multimodal human communication and using mixed reality to perform question asking in item disambiguation. And we also demonstrate statistically significant support along objective and subjective measures favoring our mixed reality feedback condition. Thank you for listening, and thank you to my co-authors.